In this video, we're going to perform sensitivity analysis in which the change happens on the right-hand side. Again, we see these two steps here that we're going to use the old optimal table, and then we calculate how the change affects the optimal table, and then we check if each variable in row 0 has a non-negative coefficient, as well as whether each constraint still has a non-negative right-hand side. If this is the case, then the current basis remains optimal. So here's the third change. We are going to change the right-hand side of a constraint. We are still using the example of Dakota problem. Now we are changing the value of the right-hand side of the second constraint, which is originally 20, to becomes 20 plus delta. Now if we look at this formula, when we change the value of a right-hand side here, it means that it corresponds to the change in the notation of small b. The change of the small b affects the right-hand side of our optimal table. And specifically, we care about the right-hand side of the constraint part. Okay, because if you recall the two steps, and then in step 2, what we need to check is that we need to make sure that if we would like the current basis remain optimal, it means that the value of the right-hand side of all constraints, which is b inverse times b, must be greater than or equals to 0. In other words, in our optimal table, we must not have any right-hand side that is negative. The logic is because we have a sign restriction saying that all variables must be greater than or equals to 0, such that whatever change we make in the right-hand side, we need to ensure that in our final optimal table, all the values of the right-hand side must be greater than or equals to 0. Okay, so we need to check B inverse and B. B inverse does not change because if you remember, the big B corresponds to the coefficient in this part of the constraint, while the one that we change is on the right-hand side of the constraint. So B inverse does not change, but the small b changes from 48, 20, and 8 to becomes 48, 20 plus delta and 8. So we calculate B inverse times B. Remember, the new B is 20 plus delta on the second row. So we calculate B inverse times B, and then we need to make sure that each of this element must be greater than or equal to 0 if we want the current basis remains optimal. And then we have these three requirements here. We take the intersection, and then we get that the intersection is between -4 and 4 for the delta. So the change can be from -4 up to +4. The current value for B2 is 20, so it means that the current basis remains optimal if the value of B2 is between 16 and 24. 16 is because 20 goes down 4, 24 is because 20 goes up 4 units, according to this allowable change. So if B2 changes from originally 20 to becomes 22, which also means that the delta equals 2, the current basis S1, X3, X1 remains optimal, but the values of those variables and also the z value change. So we may compute the new right-hand side, or in other words, the new value for S1, X3, X1 using this formula of B inverse times B. And then we plug in delta equals 2. We get the new value 28, 12, X1. So S1 equals 28, X3 equals 12, X1 equals 1. And then we may compute the new z value using CBVB inverse times the new small b. CBVB inverse does not change, still 0, 10, and 10. And then this is, the new b is 48, 22, and 8. And then we get the result that the new z value is 300. Now, what if the value of B2 changes to 30, which means that delta is 10? We see that the delta or the change is outside of the allowable range. So it means that the current basis S1, X3, S1 is no longer optimal. So let's recompute the right-hand side, and then we see that now we have a right-hand side whose value is negative. Again, we can do this by plugging in delta equals 10 to here. And then we also compute the new z value, CBVB inverse times small b, and then this value changes from originally 20 to become 30. This is our new z value. Because we have a right-hand side that is negative, the current solution is not feasible. So we append this result to our old optimal table. So the new right-hand side here, and also the new right-hand side for row 0. At this moment, we can't do anything with this table. We're going to solve this using the dual simplex that I will talk about in the later weeks. So up to now, we can only say that this table is no longer optimal because the change of the right-hand side is outside of the allowable range. But then we are going to solve this later using something that is called dual simplex. So that's the end of this video, and see you on the next one for the fourth change. Thank you.